There we go. All right, so today we're going to talk about the chain rule, and what this is, as we mentioned before, is kind of when we have a composition of function, or we have a function that's too complicated to work with comfortably, we can use this chain rule. We'll kind of look at a couple different ways of using it. And I think as we go through it, you kind of get the feel for it. It's not terribly difficult. Now the definition is kind of ridiculous looking, which I have up here. The first part just talks about the pieces that make up the chain rule, these two functions, and if they're differentiable or not. It may be a more advanced calculus course that might come into play, but we could kind of assume most things are just differentiable, like if we're doing problems with them at this point. So, just says if f is differentiable at the point u equals g of x, and this idea of u equals the inner function is something we're going to use here. And g of x and g itself is differentiable at x, then the composite function f of g of x, so again, it's just saying that g is differentiable at x, and then f is differentiable at whatever g of x was. Just different. We have a derivative. Then that composition, f of g of x, is differentiable at x, and we can define it two different ways. Okay, the first is, if you think of it as a composition of two functions, you can say the derivative of f of g of x. What you do is you take the derivative of the outer function, f prime, and then leave the inner function the same, times the derivative of the inner function. Okay, so we take so you take the outer derivative, leave the inside the same, and then we take the derivative of the inside function and multiply them together. You're going to hear me say outside in. We'll work for the outer functions. We'll kind of work our way in. We'll explain that. Another way to do it, and we'll look at both of these ways on the problem we just did on that warm-up, is to find the derivative of y with respect to x. What we're going to do is a substitution trick. We're going to take the inner function and call it u. It's called a u. Just u. And then we'll take the derivative of y with respect to u times the derivative of u with respect to x. They're both valid. They both work. Kind of use different kind of definitions at different times. We've seen that a lot in calculus, right? Sometimes prime notation, sometimes differential notation. But let's go ahead and work through our example here, kind of look at it both ways and see how that goes. So we had the function y equals 3x plus 1 cubed, right? And we looked at that by substituting it out and all that stuff. So we talked about, though, this is a composition. The inner function would be the 3x plus 1. Okay? The outer function would be the 3. Okay, so let's maybe look at the substitution method first. I think it's a little more apparent. But what we're going to do here is the inner function we said was 3x plus 1. Okay, so we're going to let u equal 3x plus 1. And once we do that, then y would just equal u cubed, correct? I pulled it out, replaced the 3x plus 1 with u. So we get that. Now, our definition here was that the derivative of y with respect to x, which is what we're trying to find, is the derivative of y with respect to u times the derivative of u with respect to x. So we just need to find those pieces then. So here, if u is 3x plus 1, so what's the derivative of u with respect to x? Just what's the derivative of 3x plus 1? 3. Yeah. This one is what's the derivative of y with respect to u. Here, we're not doing it with respect to x that we're used to seeing, so this is where differential notation really helps us. So just treat u as your variable. If you have u cubed and you take its derivative, we get 3u squared. Now, we're told by our chain rule, which we're not going to prove, but it's harder to prove than you might think, is that the derivative of y with respect to x is dy over du times du over dx. So we're just going to plug these pieces in, right? We get 3u squared times 3, which is 9u squared. Do you think a u squared would be a good answer? No. So we're going to unsubstitute. Thank you. And that's going to give us 9 times 3x plus 1 squared. So that would be our answer. Okay, now, when we did our warm-up with this, put that back on camera here, we found the answer was 20. So this, again, we expanded it. That was the rule. And then we got the derivative was 81x squared plus 54x plus 9. If I go ahead and expand this, it's going to give us this. Okay. Don't expand it, though. You don't want to. Well, we always choose things that are factored over things that aren't factored. Right? It's easy to expand. It can be really difficult to factor. So this is a better answer than the one that we got on our warm-up, which was up here. So is that making sense there? And again, if you look, right, you believe me, if I expand that, I'll be back to here. Check that off the right. All right. So that's one way to do that using this definition, right, this idea here. Okay, the other way would be to use this f of g of x, or f of g prime of x. But it says just take the derivative of the outer function, leave the inner the same, times the derivative of the inner. So if we did it that way, it would be f of, in this one, this is a kind of a weird looking rule actually, but it's f prime of g of x times g prime of x. So if we're looking at our function, y equals 3x plus 1 cubed, right, if we look at that, our inner function here, our g of x, is this 3x plus 1 because that's the inside, right? That's the thing that we do first. The outer function is what we're going to do first. So if you have something cubed, how do you take its derivative? Well, you take the cubed, you put it out front, and you reduce the power by 1. So that tells us then that y prime would be 3, leave 3x plus 1 the same, times 2. Right, that was this part. Right, I just dealt with the cube. I just dealt with the cube, the outer function. And then we're going to multiply it by the derivative of the inner function. I might not do this step all the time, but so again, put the 3 out in front, reduce the power by 1, and then we go ahead and take the derivative of what was inside. So that's going to give us now y prime equals 3x plus 1 squared times 3. Yeah. And then we get y prime equals 9, 3x plus 1 squared, which we see is the same answer, right? So we did it basically 3 different ways. Right? But these are equivalent. They just look a lot different, but it's the same process, depending whether you do the u substitution, whether you do outside in, which is kind of what we did here. This is a great way to start it, but like probably tomorrow, definitely next week, we'll look at ones where there might be 3 or 4 links to the chain, right? Like you got a function and a function and a function and a function. This gets really tedious because you keep having to do substitutions. If you can just start from the outside and work your way in, you're going to be in pretty good shape there. Okay, a couple examples here. And again, we could either do the outside in or we could do the substitution. Maybe we could do one of each if you want. It doesn't really matter. Look at them different ways. This first one here is y equals 2x squared plus 5 to the 7th. So if we just want to look at this sort of as our outside in thing, the first thing we think is we have a thing raised to the 7th power, correct? Or you can even think of it as u to the 7th power. If I had u to the 7th, I would get 7 times u to the 6th, correct? You could either use u and u substitution, or you could just write the inner part. So let's see, the derivative of y with respect to x, again, if you put y prime, that's fine, would be 7 2x squared plus 5 to the 6th, right? And then we're going to take the derivative of the inner function, which is 2x squared plus 5. I'm going to put that in a parenthesis because a lot of times you'll get a couple terms. Here we don't. But the derivative of 2x squared would be 4x. The derivative of 5 would just be 0. We really should put this over there with the 7, I think. So let's say the derivative of y with respect to x is 28x, 2x squared plus 5 to the 6th power. Did we get that? Yeah? Did you want to see it with u substitution? We could do that. So if we look at it with the u substitution, let's scoot this down a little bit here. So this was sort of the outside in technique, right? Which is probably where you're going to head towards. But let's say that we're not okay with that. Let's say we're going to say, let's let u be the inner function, 2x squared plus 5. Right? Then our y would just equal u to the 7th, correct? So that's, again, just a nice substitution. It's a great way to kind of slow things down and really be deliberate about it. It's a good thing to do. So now we know that our rule, hopefully remember that our rule was dy over dx is dy over du times du over dx. Now the proof is not this simple, but you could kind of think of it as like the du's cancel out, right? If you multiply these, you'd get back to here. The problem is you have to, to prove it, you have to prove that d of du is not equal to 0, which, that's above the scope of what we're doing here. So we're going to need to take the derivative of u with respect to x. So du over dx will be 4x. Again, just using our old power rule. And then dy over du would be 7u to the 6th. Again, we're just taking the derivative with respect to a different variable. Just like when we did position, velocity, acceleration, we did the derivative with respect to time, right? Not a new thing. And then we'll get the derivative of y with respect to x will be the product of these two pieces. So it would be 7u to the 6th times 4x. Now again, we don't want u's in our answer at all, right? Because u was a substitution that we made. We have to undo it before we give our answer. So that's 28x times u to the 6th, which is 28x, 2x squared plus 5 to the 6th, which would be the same thing that we had before. Same process, different steps. Okay. If this, definitely this I think is a little more systematic. It might appeal to some people more. Probably you'll head towards that as we move along. Questions there? It's good they're both the same answer, right? If they're different, that would be a concern. So let's look at this next one here. Y equals 10 times the square root of 3x plus 5. First thing is we don't want a square root, right? That's not a thing that we want. So let's rewrite that as y equals 10 3x plus 5 to the 1/2. Now, in this case, 10 is just a constant multiple, so we can just leave 10 kind of outside and then multiply it back in. It's just going to sit out there and multiply by 10. If it were its own function, then we'd have to use a product rule, which we're not really there yet. We're just looking at the chain rule today. So what we can do is if we just work from, well here, let's use the u this time. Let's kind of switch it up. So if I want to do the substitution, we see our inner function is this 3x plus 5. So let's let u equal 3x plus 5. Then that means y would be 10 times u to the 1/2 power. So see, the 10's getting included right there. It's all good. Does that make sense? Don't leave it like it doesn't go away or anything. It's still there. And then we'll take the derivative of u with respect to x is 3. And then we'll take the derivative of y with respect to u is 10 times 1/2 times u to the negative 1/2. Again, just the power rule, right? Old power out front, subtract 1. So this will give us 5u to the negative 1/2. Now we know that our derivative is going to be the product of these two. Yeah. So we multiply those together. We get dy over dx would be 15u to the negative 1/2. Our last step would be to unsubstitute. And we would get the derivative of y with respect to x is 15, 3x plus 5. Oh, that's not a very good number there. To the negative 1/2 power. That would be great to express it that way. Looks fine. You probably, though, would also see it as the derivative of y with respect to x would be 15 over the square root of 3x plus 5. That would be a really common way to see it also. So again, just either one's acceptable. Just make sure that you're able to see that they're the same. I did want to look at that when we kind of ran out of space. I did want to look at it if we just did the outside in kind of technique, right, to kind of compare that. So for that one, if you have y equals 10, we still need to get rid of the square root. So we'll still say the 1/2 power. But in terms of outside in, 10 is just a constant multiple, right? So it's just going to multiply by 10, just do its thing. Right? We learned one of our first derivative rules is we could just pull the 10 out and multiply it by the derivative. So then I'm going to take the derivative of this thing, which is to the 1/2 power. So I'm going to pull the 1/2 out in front, drop the power by 1. This will stay exactly the same inside here. Okay? It's the u, right? It's what we did over there. So it's going to be 1/2 3x plus 5 to the negative 1/2, and then times the derivative of 3x plus 5, which is 3. So that gives us 15 3x plus 5 to the negative 1/2, which is what we saw before. Or again, you could say 15 over the square root of 3x plus 5. Would be how that would look.